morning, everybody. So I'm thanking Victor for giving me an opportunity to present my case study in front of all you experts of Indian pulp and paper industry. So my name is Katuri Joseph, working as senior manager in ITC Limited unit Bhadrachalam. So I'm going to present our practical experiences with ozone bleaching. If you see the ozone, it's a environmental protector. So as everybody knows, it will protect us from the harmful UV rays coming out of the earth, and so it is protecting us. But if we see over the years, from 19th century starting, so the average at temperature is around -2 degree Fahrenheit. But within 1 century, it is, sorry, I'll use the pointer. So over the century, it is increased up to +3 degree Fahrenheit. So it clearly shows that there is increased global warming, and it affects on the human health. It is also affecting the plant, trees, and aquatic life also. It is affecting very badly. So this is the introduction for the ozone and its how it is protecting the environment and humans. Come to our subject. So now I am going to cover the crowd pulping impact on the environment and the technology upgradation we did at ITC Limited, and crowd pulp bleaching sequences and the various chemicals we are using it, and the evolution of the bleaching chemicals and operating parameters to produce ozone, as well as the ozone bleaching sequence, what are the operating parameters to be maintained, and the concerns and the challenges we have faced from starting, and how we have eliminated each challenge, and finally end up with the advantage of the ozone bleaching. If you see the impact on the environment with respect to crowd pulping, there is two verticals like raw material plantation and transport, and pulp production from the wood in order to make the pulp and paper products. If you see raw material as a source from the breeding to plantation, raw material we are using fertilizers, and in the harvesting and transportation we are using diesel. So these two activities are releasing so many pollutants and leading to eutrophication, global warming, smog, and acidification of the air. And in the pulp production process, the sources are like pulp production, energy generation, chemical recovery system, and wastewater treatment. So in the pulp production, we are using various bleaching chemicals. This is increasing the absorbable organic halides, and it is leading to the toxicity. And the water usage, it is leading to eutrophication, and again energy generation in the boilers, it is leading to global warming, and again chemical recovery plant, it is leading to acidification, smog, and so in this juncture, all the mills in pulp and paper industry has or had implemented many technologies and many initiatives took up to save the environment. With respect to ITC, we at ITC since 1978 we are using chlorine bleaching, and 2003 we moved up to CO2 usage with ECF, and 2008 we moved to ozone with light ECF. In recently 2008 we have implemented OptiC model, wherein it has improved the cooking sequence, and also in the screening we have eliminated almost negligible solid waste from the screening section. In 2020 onwards, we implemented Industry 4.0 initiative, historian and all, where to improve the quality as well as reducing the bleaching chemical consumption. And this year we are coming up with new single bleaching line, where it is reducing the bleaching chemicals as well as the effluent generation. You see, crowd pulp bleaching, just I will give the overview. Its purpose is to remove the lignin content and protect the cellulose and hemicellulose as much as possible, and it is to brighten the pulp and to minimize the environmental effects. Common chemicals, as we know, it's chlorine, chlorine dioxide, sodium hypochlorite, oxygen, nitrogen peroxide, and ozone. So there are different sequences and various sequences available bleaching to process. So we at ITC were following D0Z, UPD1, and D0Z, D1, and P. And end products are like printing paper, uncoated packaging board, coated packaging board, tissue paper, decor paper, and end usages like notebooks, textbooks, packaging of cosmetics, medicine and food products, packaging, tissue paper and greeting cards. While evaluating the bleaching chemicals, so definitely we need to look at the environment, because there are various regulations from the government and local lobbying, and water also there is a limited supply, availability also less. So one of the driving forces is the environment to reduce the color in the effluent, COD, BOD reduction, AOX content reduction in the effluent, and water consumption reduction, and also implementing water recirculation backward recovery from the EOP stage. If you evaluate the various bleaching chemicals with respect to their efficiency, with respect to their reactivity, selectivity, and environment, so chlorine has a higher reactivity, higher efficiency, higher reactant selectivity, but it is badly affecting the environment. And also sodium hypochlorite is badly affecting the environment. But if you see the ozone, it is having higher efficiency, higher reactivity, and less medium selectivity, but it is very good with respect to the environment. So that is the reason, even though it is having higher reactivity, if you use at the early stages of bleaching, where we are having a high lignin content, so preferentially it will react with the lignin and it will give the benefits with respect to bleaching chemical consumption. If you see the ozone, it's 3-atomic oxygen molecule and its redox potential is 2.07. When compared to other oxidants, it is having the highest redox potential. It is pungent and blue in color, strong smelling gas. So ozone, as the Greek name is smelling, so ozone means smelling. So how we are producing ozone is, there is oxygen gas, there is a to this oxygen gas will apply energy in the ozone generator. This oxygen molecule is split into the free oxygen atoms, and this electrical field, this oxygen atom will gets bond with oxygen molecule, and thus it become ozone. If you see how we are applying electrical field, this is the ozone electrode. So in the generator, almost we are having 20,000 of electrodes. So I am talking about one electrode. This is the one electrode. Just above this, we are having a epizone mesh, and before that we are having a gas distribution sleeve. Actually, the oxygen enter through this, because this gas distribution sleeve, oxygen will enter this, and this epizone mesh will allow the oxygen to convert as a ozone. Above this oxygen, epizone mesh, we are having a dielectric tube. It's a borosilicate glass. This is the electrode. All these electrodes, 20,000 electrodes, are in a generator where it is having a shell and tube heat exchanger like thing. It is having tubes of 20,000. So in each tube, these electrodes are inserted. We see at the macro level, this is the electrode, this is the gap, and this is the distribution sleeve to allow the oxygen into the electrode, and there is a slight gap, and over that we are having a dielectric. And between dielectric and the tube there is a gap again. So whatever oxygen we are giving inlet, partially it goes into the electrode and remaining goes as such. Why? Because we need only 10 to 10.5% concentration. So all these electrodes are connected to a high voltage power supply, which is grounded. Both sides are closed with the dome. And during the ozone generation process, there will be heat generation. To dissipate that heat, we'll give cooling water, which is chilled water at the inlet and outlet. This is a typical ozone reactor in detail. So this is a generator. It is having two sections, section 1 and section 2. Section 1, partially ozone will be converted, and remaining oxygen also converted in the second section. So these are the electrodes, one side. We'll call it as power supply 1 and power supply 2. So all these are connected like this with a high voltage connection. Rooms are closed like this. These are power supply units. It is having a rectifier section, inverter section, and setup transformer. So normally we will give 415 kilo 14 volts with 50 frequency. At the outlet of the step-up transformer, the frequency is 1000 Hz. Frequency will be 1000 and voltage is 5.5 kV. For each electrode we will give 5.5 kV. So we see here, this is the oxygen inlet and this is the ozone outlet. This is the cooling water system inlet and outlet. For the power supply units also, we need to maintain the cooling system. For that also, we are having chill water inlet and chill water outlet for the transformer. So we see the three pillars of the ozone production. One is feed gas, which is oxygen and the energy, and the cooling water system. Feed gas is like you can give liquid oxygen or oxygen with 95 plus purity. The conditions are like we need to maintain dew point of minus 70 degrees centigrade below. And it should contain slightly nitrogen. Why? Because in the presence of nitrogen, it will make a N2O5 layer in the epizone mesh and it allows the oxygen to make as ozone. Cooling water supply, we need to maintain temperature of 6 to 9 degrees centigrade and should be free from the hotness. In the power supply, as explained, 415 volts, 50 frequency with 3 phase. So typically we will achieve power consumption of 16 to 15 kilowatt hour per kg of ozone produced. So our bleaching sequences, we are having two Weber lines, one with D0 stage, ozone stage followed by EOP, peroxide and D1 stage. The second line, it is D0 stage followed by ozone and D1 and peroxide. This is the typical our ozone generator. Then the generator is within the container, the oxygen inlet and ozone outlet. So oxygen pressure will maintain around 1.25 with 95% purity of the oxygen. At the outlet, 10.5% ozone we will produce. This is water inlet and outlet. This is the power supply. When coming into the bleaching, this is the ozone reactor. It's hardly 5 to 6 meter reactor, horizontal reactors. It's around 2 meters dia. So it needs the process conditions like inlet pulp pH should be 2.5 to 3.5 and it needs higher consistency. That is the reason press outlet, previous stage press outlet, directly will be feed into the ozone reactor. Here the gas and the pulp is the counter current. The gas will flow like this and pulp will flow like this. Whatever unreacted ozone, slight unreacted ozone will be there, that will scrub it, minister will remove the whatever water moisture is, will remove it and in the heat exchanger will maintain the temperature. Then it will go to the COD, catalytic ozone detector, where MgO crystals are there. That will convert excess ozone into the oxygen. Then finally it will go to the atmosphere. But here the challenges are like availability of ozone generators will be a challenge because of various issues. And ozone, it needs a very low temperature, below 55 degrees centigrade. So maintaining low temperature is a challenge because the previous stage is D0 stage, where we are maintaining temperature of 65 to 68 degrees centigrade. Maintaining lower pH, lower temperature is a challenge. And pulp consistency, it should be around 35 to 40% consistency. Whenever this pulp consistency gets lower, the reactivity goes down and we will not get the required brightness. So from the starting, the various challenges you have faced like generator tripping, ozone generator tripping, because of the inlet oxygen pressure variations. For that, we have provided a regulating system for the pressure with a vent valve. From the oxygen plant also will maintain the pressure as well as the reactor inlet, ozone generator inlet will maintain the pressure control system. So that has eliminated the pressure fluctuations and also insufficient cooling water system because of the jamming in the system because of the dust entry. For that, we have provided self-cleaning filters. And also insufficient cooling for the transformers. We have power supply units are there. For that we are having a transformer. There we maintain the cooling system. For that also we operate with from different chiller to get the continuous supply of chilled water and without affecting the ozone generation. And one more thing is tripping the power supply units to due to malfunction of the temperature sensor. In the PSU, the ambient temperature AHU, it will maintain by AHU. That ambient temperature is also very important. But sometimes it is malfunctioning. Then we have shift the sensor in the right direction with multiple iterations. Then it has led to non-malfunction of temperature sensor. Volume as a whole, before the ozone availability is around 84%. Now it is improved to 99. And production itself 150 kg per hour to the maximum capacity of 220 kg per hour we are achieving with a concentration of 10.5%. There are other operational issues in the fiber line, like sealing in the press and channels, filtering channels. It is leading to high watt pressure, improper washing, carryover of the chemical and higher chemical consumption. Because of this cleaning, at least once in a month we are forced to stop for 24 hours for the scale cleaning. And during scaling issue, we used to purge lot of water to purge out the scaling. This is mainly because of the calcium oxalate formation in the ozone stage. Our original sequence is PO2 stage followed by ozone, D0, UOP and D1. Whereas directly into the ozone stage, there is a high calcium input through the pulp, almost around 12,000 ppm. And pH also from the ODL we are maintaining around 10.5, 10.8. pH for the ozone we are reducing up to 2.5. There is a update reduction in the pH. It is also leading to the scaling and also the high bar content in the chips. So later on we have modified the sequence with D0 in the first stage to purge out the calcium and followed by ozone, UV and D1. As a result, low calcium content is entering into the ozone stage and pH also the swing is not there 3.5 to 2.5 and also whatever bar content we are using, now we are using 100% debar wood. So as a whole there is a huge reduction in the scaling formation. Now almost once in a year, during once in 6 months only we are cleaning these presses. And one more challenge is to maintain the lower temperature in the ozone reactor. You need to maintain around 55 to 50 degree below, whereas D0 are coming at 65 to 68. For that, what you have done is, whatever steel body you are using the D0 and D1 stages, the inlet temperature is 15. So we have introduced one heat exchanger. Already it is there with outlet CO2 temperature of 35 degree. It is being heated up with hot water and outlet temperature is 45 by adding additional salt water to maintain the temperature as well as the scaling reduction in the ozone stage. And other issues are like in the ozone, whatever excess ozone is there, slight excess ozone is there, it can escape into the environment. So how it is safeguarding the people is the entire system is under the vacuum. There is a fan here, the COD outlet, we are having a fan. So it will suck the entire excess gas through this. Whatever excess gas is there will go to the scrubber to remove the fiber particles and we will maintain caustic to neutralize the gases. And at the outlet we are having a ozone destructor system, MgO crystals we are having. So this will convert ozone into oxygen. This oxygen is venting into the atmosphere. So whatever oxygen is coming out, it's around 40% purity. This can be used in the ETP treatment or ODL stage after compression. And also one more challenge is like at higher temperatures and higher ozone concentration, the ozone can catch fire because of the pulp. So that is the reason we reduce the concentration from 10.5 to 12 and maintaining concentration around 36 to 38%. Since the insertion of the ozone generation system, we cannot face any problem of ozone fire or this thing. And each area in the ozone generator system, the generator and the reactor area, we have provided adequate ozone detectors so that it will trip the system whenever any leakage is there. And also respiratory systems are provided at each area. If you see the benefits of this entire ozone bleaching sequence, the effluent discharge is reduced from 32 to 13 in the pulping section, and AOX level is reduced from 0.24 to 0.006 in the final effluent. And if the chlorine dioxide consumption 60 kg to as a chlorine to 30 kg now, and hydrogen peroxide 7 kg per ton to 4 kg, and water consumption in the bleach plant from 25 meter cube per ton to now it is 12 meter cube per ton, and COD in the bleach plant effluent is 29 kg per ton to 18 kg, and final effluent discharge color is 250 units to 120 units. So these are the benefits we got with respect to the ozone bleaching and also chemical consumption reduction. Thank you very much.